Good morning, everyone. Welcome to Lunch with a Scientist, your opportunity to get to know another awesome scientist and see some of their research. Today, in just a minute, I'm going to be welcoming Dr. Julia Kelson. And first, I'm going to tell you a little bit about her talk as a teaser. So she says, we are currently witnessing one of the most dramatic climate change events in the Earth's history. This begs the following question. How has Earth's climate changed throughout geologic time? So today you're going to get a glimpse on what that means, and you're going to hear from Julia Kelson. Welcome, Julia. Hi, how are you today?
Doing well. How are you?
I'm good. Where are we talking to you from?
I'm in Ann Arbor, Michigan.
Great. So it must be after lunch for you.
It is. Yeah, it's a couple hours after lunch. We got some fall colors. A little Beautiful. Bit crisp fall air. Yeah.
Well, thank you so much for being here. So Dr. Julia Kelson's research seeks to reconstruct climate during the so-called hothouse periods of Earth's history, which corresponds to high concentrations of carbon dioxide in the atmosphere. She uses the stable isotope geochemistry of ancient soils to understand the evolution of temperature and aridity in terrestrial environments. She's a California native with a passion for granite landscapes. She has a BA in Earth Sciences from Dartmouth and a PhD in Earth and Space Sciences from the University of Washington, Seattle. And she is currently a National Science Foundation Earth Science postdoctoral fellow at the University of Michigan, Ann Arbor. And we are so excited to welcome Dr. Julia Kelson. I'll let you take it away.
All right. Thanks for that nice introduction, Leah. And hello, everybody in the Facebook Live audience. I can't see you, but I'm glad that you're there. So I'm Julia Kelson. I'm a postdoctoral researcher at the University of Michigan. And essentially what that means is that I get to do research on questions that I find interesting full time. So I get to think about interesting questions in geology and then plan how to answer those questions. And so what I'm working on right now and what's motivated a lot of my research is understanding climate change in geologic time. And I do that by using soil geochemistry. And more specifically in today's talk, I'm going to tell you about the project that I'm working on this very second that's trying to identify aridity and how aridity has changed through geologic time, specifically using evaporation and the evaporation that we can detect with stable isotopes of soil carbonates. And hopefully that explanation will make a little bit more sense by the end of this talk. So again, just the kind of big picture motivation for my research is that the Earth is warming right now. And this here I'm showing you a classic climate science figure that was first published in 1998. And this is called the hockey stick figure because it looks like a hockey stick. So starting in 1900 with the time of the Industrial Revolution, when humans started emitting greenhouse gases, we can actually measure that there's been an increase in average surface temperature correlated with the increase in greenhouse gases. And so scientists actually predicted this, and we've been able to measure it, and we know that it's happening. And we've probably learned about this in our sciences classes, but as a brief reminder, we know that greenhouse gases like carbon dioxide act to warm the Earth's surface. And so as most of the heat on the Earth's surface comes from the sun, and that comes in and hits our Earth as incoming solar radiation. And then when it's absorbed by the Earth, it changes wavelength and tries to escape as thermal radiation of a different wavelength. But turns out that carbon dioxide and other so-called greenhouse gases are really effective at trapping that outgoing thermal radiation. So as we increase the concentration of greenhouse gases in the atmosphere, we increasingly heat the surface of the Earth. So we're confident that this process is affecting our current Earth climate. What we're less confident about is exactly what magnitude temperature change we might expect to witness as a result of those increasing concentrations of greenhouse gases in the atmosphere. And in addition to the temperature response, there's kind of a whole series of other climate responses to this, into what we call greenhouse gas forcing, or the increase in temperature. And so we've already, this is probably intuitive for those of you in California, especially given this current wildfire season. We know that there are going to be other climate responses to this increase in temperature. And one hypothesis perhaps is that wetter zones will get wetter and drier zones will get drier. And so we might observe increases in regional aridity that might result in something like more intense and severe droughts in the future. But so my approach to trying to answer these questions is actually by looking at the past. And so I'll explain to you why I think the past is at least one way or one key to understanding the future warming. And so here I'm showing you a figure of the current best understanding of climate of the deep ocean. Is really, I'm showing deep ocean temperature, but climate of the past 60 million years of Earth history. And so on the x-axis here is time in millions of years. So we're here at 0 million years. We're just this little blip. And then on this y-axis is the oxygen isotope composition of benthic foraminifera, which is a bit of a mouthful, but they're these shells, these organisms that live in the deep ocean that have carbonate shells. And so scientists have drilled the ocean crust, or the sediments on the bottom of the ocean floor, and then reconstructed or measured the oxygen isotope composition of those little creatures to reconstruct the temperature at the time that they formed. And so we can create this this curve of what we think deep ocean temperature was like through millions of years. And you can see that through this time period, Earth has gone through quite a bit, and that this current climate state that we're in is actually very different than the one that we experienced millions of years ago. It's actually one of the colder climate states in recent geologic history, where we didn't see ice sheets until about 30 million years ago. So this blip here is the start of ice sheets. But the periods of time that I'm most interested in are these periods of time up here. And what I find fascinating about this is that it's so warm. And so on this y-axis, you can see effectively what the temperature changes compared to modern. So this is something like 12 degrees Celsius warmer in the deep ocean than modern, or even more than 12 degrees Celsius. And what's important about this time period is that this is about the amount of warming that scientists predict that we could be headed towards. And so this star is approximately the temperature change that we can expect to witness under what's called representative concentrations pathway 8.5. And that's essentially business as usual greenhouse gas emissions. So if we continue to emit greenhouse gases at the same rate and increase our emissions at the same rate as we currently are, then we can expect to witness this much warming in the next century. And so this highlights this period of geologic time as a really key period to understand, because we can use it as an analog for future climate, and it can also be used to illustrate end member conditions. So this is the consistently warmest period of time in the past 60 million years. And I put this back up to remind myself to explain to you why I showed this goofy little alligator and palm tree earlier. So this time period called the early Eocene, we qualitatively knew was quite warm because scientists in the 1980s, I believe, found evidence for palm trees and alligator fossils at really high latitudes. So even in the Arctic and places now like Greenland that's covered in an ice sheet, we found deposits of this age that have alligator fossils. So we know that it was quite warm, that it was a tropical forest at high latitudes. But the question is, how did it get to be that warm, and what did that mean in terms of other climate states, other aspects of the climate system during that time period? So goodbye, alligator. Okay, so what I'm going to focus on is how the water cycle changed, and more specifically, how regional aridity changed during that time period. And actually, most of the question that I'm going to answer is, how do we measure regional aridity? And ancient water cycle. As you can imagine, you can't necessarily, it's really difficult to reconstruct aridity that long ago when the water that we're interested in is no longer there. And so I'm going to tell you how I use soils to reconstruct aridity. And more specifically define aridity, I'm interested in the balance between evaporation and precipitation. So in this water cycle diagram, the balance between precipitation that rains on a specific spot and evaporation that comes up from that specific spot. So how has that balance changed? And conveniently, I can use oxygen isotopes of water to track evaporation, this process here. And so then we can start to understand the water cycle. And so in modern water, you might imagine that it's pretty hard to identify whether or not something's been evaporated just by looking at it. So here's this glass of water. It's half full. You can't tell just from looking at this glass of water whether or not I drank the first half or whether it's been sitting on my desk for 2 months and it evaporated. But I can tell you, but I can use water isotopes, so the oxygen isotope composition of that water. I can tell you in a couple hours which of those two options happened. And so to explain how that works, I'm going to go back. Here's the chemical formula of water. Here's 2 hydrogen atoms and an oxygen atom. Okay, but I'm just going to look at the oxygen atom for now, and I'm going to talk about the isotopes of an oxygen atom. So an isotope is an atom that has extra mass in the neutron. So a normal oxygen atom, like the one on the left here, has 8 protons and 8 neutrons in the nucleus, and that leads to a total atomic mass of 16. So you add 8 plus 8 and you get 16. But a heavy oxygen atom, which is rare, this is about 3% of all oxygen atoms look like this one, has 8 protons and 10 neutrons in the nucleus. And this might seem like a really small detail, but it's extremely useful because it turns out that this slight difference in mass means that these 2 molecules behave very differently, and that there's a slightly different amount of energy required to move these different atoms around during phase changes. So it actually acts as a natural tracer for different changes in phase and as a natural tracer for the water cycle. So again, here's this kind of normal water molecule with a mass of 16 and the heavy water molecule with a mass of 18. And so usually we refer to the mass 18 because it's the rare one, and that's the molecule that we're going to track through geologic time and watch how this one moves. And to give you an intuition for how this works, and more specifically in the process that I work on, is evaporation. And this works because those heavy isotopes, that oxygen 18, or I'm using this notation D18, delta 18O, which tells you that it's the ratio of 18 to 16, but we're just, again, tracking that heavy isotope. But those heavy isotopes are preferentially left behind in the process, like evaporation. It's just harder to lift a heavy item compared to a light item. So if your ocean water, we set to be 0 per mil, and don't worry about the notation, but we set to be 0, then water vapor that evaporates from that ocean water is going to have an oxygen isotope composition of something like -10. And so we can track this process. We can track how much evaporation occurred both in modern waters by measuring that oxygen isotope composition. Okay, so this water I actually drank half of. So if it had started as seawater, this would be 0 per mil. Versus if it had sat on my desk for a month, it would probably be something like -20 per mil, where it wouldn't have the opposite. It would have positive 20 per mil, where all of those light isotopes left the water glass. And what's left is what we call enriched in heavy isotopes. Okay, so that's in modern water. But like I said, the water that I'm really interested in studying doesn't exist anymore because it is evaporated 50 to 60 million years ago. And so we have to get a little bit more creative in what we use as a record for aridity. And so what I use in my research are soils, and these are one of the best geologic archives of ancient climate that we have. And this picture that I'm showing you here is of what's called the John Day Formation in eastern Oregon. And each of these stripes on this hill slope, each of these tilted stripes are an ancient soil, or is an ancient soil horizon. And so we can look at the minerals that form in each of these ancient soil horizons and start to understand the climate under which these soils formed, as their soils are just at the really, really thin surface of the earth. And so if it rains more, the soil's geochemistry will reflect that. If it's more arid, the geochemistry will also reflect that. And so we can go back and find places where these kind of ancient soil horizons exist from the time period that we're interested in, and look at the isotopes in these soils to understand the evolution of something like aridity through geologic time. Okay, and more specifically, I use a mineral called calcite or calcium carbonate. So if I use those terms interchangeably, they're the same thing. And I look at the oxygen isotope composition and also the carbon isotope composition, which I did not explain but could later. And so this mineral looks something like this. It's kind of an unattractive mineral. It's a little blob of calcium carbonate, and then this is a picture of kind of what that carbonate looks like in an outcrop or in a rock, where this what's called a nodule of carbonate forms in place. And so we can go back and collect, or we can go out into the field and collect these soil carbonates. And what makes them useful is that they form in soil water. And so the isotopes of that mineral, the isotopes of the calcium carbonate, will record the isotopes of the water from which they grew. And they'll also record other information that I'm not going to go into a lot of detail about, but as you can see on this this diagram of CaCO3, there's one carbon isotope and 3 oxygen isotopes. So this carbon isotope can also tell us a lot about the vegetation that under which that soil formed. It can also tell us something about the concentration of atmospheric CO2 under which that soil formed. But I'm really interested in the relative proportion of these oxygen 16s versus oxygen 18s, again, because they can tell me about evaporation. Okay, so the method that I'm working on is actually fairly new. We are witnessing we're under a period where we're seeing increased precision in laboratory sciences, so we're able to measure increasingly small signals, and which means that we can finally go after big questions like how has aridity changed and how much has evaporation changed through geologic time. And so the question that I'm attempting to answer right now is how the oxygen isotopes of modern soil carbonates changes in modern environments. And so this axis here on the Y is increasing evaporation on the bottom and then decreasing aridity on the x-axis. So the hypothesis that I had when I started was that in modern soils, I would see less evaporation in soil water compared in these more humid areas, whereas in an arid place, I would see more evaporation. So something like desert regions would fall in this quadrant, and a soil that formed in a humid place would fall in this kind of quadrant. And so my strategy is to measure this in modern soils first, so that we can then use it, then we can apply what this tool, essentially it's called a proxy for aridity or evaporation in ancient soils. Okay, so the strategy that for this study that I'm going to show you the results from, I've collected modern soils from a range of environments, from arid to humid places, and then I measure their oxygen isotope composition and build this graph. So this is proxy development work, essentially. And so here's some pictures of some of the places that I've gone out and collected soils from in the past year. This was me in the Mojave Desert in August of 2020. So just a couple months ago, I went out to the Mojave Desert. It was about 106 degrees by 10 a.m. when we stopped doing our field work. So we got up bright and early to get out and collect these soils before the heat of the day. And it's always a good reminder. It's always kind of fun to do field work in really, really hot places when I'm trying to understand hothouse climates. It's a good reminder that it could be much hotter, probably was much hotter during the Eocene in this time period that I'm interested in, which is hard to imagine when it's 110 degrees. But here I am on this. This is a modern soil surface. This is me collecting the sample. And this is the soil pit that I dug with my field partner. And then here in this picture, I'm pointing at that beloved soil carbonate, which is, again, not the most distinct mineral, but it's kind of this white coating that's around the clast. And so this is what I was after. I actually took this clast home and put it in a bag and then started to analyze it. And here's some pictures from soil in Livermore, California, this is the Bay Area of San Francisco. And you can tell from this picture that this is a very different environment than the Mojave Desert. There's fresh green grass. This is, I think, December. So a little bit different time of year. There's water. I know these hills are all brown right now, but you can tell that this is not quite as dry of an environment as the Mojave Desert. And the soil looks a little different too. It's this kind of thick black soil with these small little nodules that I'm pointing to in here. And so this tells you something about, you can already tell that this environment is pretty different. There's more organic matter in the soil that's making it a darker color. And then I can also predict that the oxygen isotopes of this calcium carbonate is going to be pretty different. Like the prediction would be that these would be less, they would look less evaporated than the soil carbonates in the Mojave Desert, where it's pretty dry. And then this is kind of an in-between place that's close to where Headwaters is based out of. I went to Sierraville, California, again in December. You can tell because there's snow on the ground. And I didn't have to dig a soil pit here because there was this road cut, which was very convenient. So I drove up to this road cut and then logged the soil profile and collected. Again, here I'm pointing at that my favorite white mineral calcite that's in the soil. And so these are just kind of a snapshot of 3 of the environments that I've sampled. You can tell that they're pretty different environments and probably they have different aridities in the modern. And so the goal is that I could use these to calibrate the past. Okay, so then once I have these soils, how do I measure their oxygen isotope composition? So here's a funny picture because I did most of my field work in December, and then in the spring was when I was planning on doing all my lab work. And then, of course, like everything else in March, our lab shut down to slow the spread of COVID. And then this picture I took of myself in June. It was my first day back in the lab after many months of shutdown time. And we were required to wear masks, which at the time was, I mean, people weren't really, or the use of masks hadn't been widely accepted yet. Of course, now we wear a mask for everything. But this felt odd that I had to wear a mask in the university, and I also had to wear a lab coat for the first time, which usually I don't work with toxic substances, so I don't have to wear a lab coat. But this was our safety protocol during COVID. But I was grateful to be able to continue to do lab work in those really early days. Okay, but here's a picture of the instrument that I work on. And I love this picture because it's about as pretty much looks like science. If you were going to take a picture of a crazy laboratory, this is what you would get. And indeed, this is what the laboratory I work in looks like. And so this is the purification system that I use. So I actually put the carbonate starts over here where I take that rock mineral and I digested an acid over where it says poison. I just told you that I don't work with toxic materials. That was kind of a lie. But you digested an acid here and then use these series of valves and what are called traps. So here are these loops that the gas passes through, these different loops. And these are ways to purify the gas that's coming off of this, to turn the sample into gas and then purify that gas. And so it's a series of multiple chemical reactions to get to our measurement state. So first we digest the calcite in acid and I turn it into carbon dioxide. And then you have to purify the carbon dioxide gas. And then we reduce the carbon dioxide with an iron catalyst and turn it into water. Then I fluorinate that water and turn it into oxygen gas. And then finally, we get to measure the isotopic composition of that O2 gas. And this on the right-hand side here is a mass spectrometer that we use to measure the isotopic composition. So the sample moves from left to right. And the preparation time for a single analysis takes about 2.5 hours, and the analysis time on the mass spectrometer is about 2 hours. So it's quite a bit of time and effort to produce this data. But I think it's worth it because the results are looking to be exciting. So as a reminder, here's the graph that I'm working on right now. I predicted that there would be a relationship in modern soils where I would see increasing evaporation in the oxygen isotopes of modern soil carbonates in more arid places. And this kind of looks like it's true. So yes, it's true, but this relationship is probably more complicated. So it's certainly not a single line where we see continuous evolution with decreasing aridity. But instead, what we observe is that in these dry places, like these colors here correspond to where I collected the soil carbonate, where the key is on the right. Then these dry places like in Nevada, and this sample is from the Atacama Desert in Chile, which is one of the driest places on Earth. So over here, we definitely see that the soil waters formed under extremely evaporative conditions. And so we could use this to detect an extremely arid environment in the past. And then over here on the right-hand side, it does look like these soil carbonates that were collected in Texas and in Argentina, or I'm sorry, this sample is from Myanmar. These are forming under conditions that are not really evaporated. So this would look something like a humid climate. The in-between is where it gets complicated, and it certainly looks like there's more of a process threshold than a linear relationship, where there's some soils that are not evaporated at all, some soils that are extremely evaporated, and then a lot of soils that are in between. And so I think that this isn't a perfect proxy, but I think it will help us to it certainly can be used to detect aridity and certainly extremely arid environments in geologic past. So I'm not going to show you any results from the geologic record because I don't have them yet. So that will be the next task the next year, is to use this relationship that I've developed in modern soils to apply it to ancient soils that I've collected and understand how aridity has changed during ancient global warming events. And here I'm showing you a picture of early Eocene soils in Big Bend, Texas. And again, each of these colored bands, the white and the blue and the purple and this yellow, are different ancient soil horizons. And so you can collect soil carbonates up this section and hopefully produce a record of how aridity has changed through geologic time. So to sum this up, the geologic record offers a valuable perspective of climate change in hothouse worlds. I'm interested in the early Eocene because this is one of the time periods that we know is extremely warm, and there's a lot of carbon dioxide in the atmosphere. So we think that these time periods are good analogs for future warming. And soil carbonates are one of the few tools that we have to investigate those ancient climates, especially on land. So I showed you that we have a pretty good record of how temperature has changed through the deep ocean, but on land, the record can be more difficult to find. But soil carbonates are one of the few tools that we have to reconstruct ancient climate in deep time. And what I'm working on right now, and hopefully what you feel like you have an understanding of, is developing stable isotope tools we need to be able to interpret those archives that exist. Those rocks are out there and they know what the climate was like. It's just a matter of us figuring out how we can read the climate record from those rocks. I need to acknowledge my funding sources. So a lot of this work has been funded by the National Science Foundation, including my time as a postdoc at the University of Michigan, as well as my time as a graduate student at the University of Washington. So here's some funding sources. And thank you all for your attention. Here are these are Eocene alligators. This is a joke that a friend of mine developed, but all of these alligators are laughing at this. This alligator was at the North Pole in the early Eocene, and he went on a trip to the North Pole and he brought his coat, and all of these alligators are laughing at him because he didn't know that it was already warm at the North Pole during the Eocene. All right, so with that, I'll take any questions.
Julia, thank you so much. That was great.
Yeah, you're welcome.
So fascinating to kind of take a trip back through history and then to modern times and kind of learn about what you might be studying in the future. Really interesting. So I'm going to give a few minutes here for people to comment their questions. And while we're waiting for that, I'm going to kick us off here. I'm curious, you mentioned it was really, really hot during the Eocene period. How hot do we think it was?
Right, so we think that deep ocean temperature in the Eocene was 12 degrees Celsius warmer than it is now, or more than 12 degrees Celsius warmer. But what does that translate to in terms of on land? Like what organisms would experience is a different question. So one outstanding question about the Eocene is whether or not temperature gradients were the same as they are in the modern climate state. So we know that average temperature was quite a bit warmer, but we're not sure how that temperature distribution changed. So we know that the poles were basically tropical forests, but does that mean that at low latitudes, like in the equator, was it so hot that life couldn't survive? Was it a boiling forest, or was it still a forest? There's fossils of life from the equator. Like we know that plants lived at the equator at that time period, which suggests that it was at least habitable. But the quantitative estimates of temperature that we have suggest that the temperature difference was something like a place like Seattle, Washington was as warm as Los Angeles is now. So those kind of mid-latitude places would have been as warm as low latitude places. And then everything kind of shifts hotter and hotter, where Arctic places would have also been about as warm as Los Angeles. And Los Angeles, we think, was probably also the same temperature as Los Angeles it was now.
Right. Fascinating. Really interesting. I have a question from Spencer, our program director. He says, what impacts how far back you could use these tools to estimate past climates?
Right, that's a good question. So there are a couple of things that limit our ability to go far back. The first thing is whether or not those records exist. So there are well-preserved ancient soils that go back as far as we think probably about 80 million years, so through the Cretaceous, which is when dinosaurs were around. There's a good what we call stratigraphic record. So those rock horizons exist that far back in time. But of course, the further back in time you go, the patchier that record is, just because those sediments, those rocks have been on the Earth's surface for a while, and whether or not they're still exactly where they were first placed, and they haven't been eroded or otherwise moved, otherwise buried, and then re-exhumed to the surface is a different question. So it's whether or not those records exist and whether or not they've been altered. So even if you do have a soil horizon that you think is, or that you know is 80 million years old, a valid question is, has it been on the surface for so long that it's reacted with modern waters and modern, it's called diagenesis, basically, whether or not the minerals in that soil have re-equilibrated or somehow been altered by waters and fluids since the time of their deposition. So you need to find a horizon, that exists, and then you also need to show that that horizon has not been affected since its time of deposition, that it still records the climate at the time of its period. And yeah, those are the two primary limiting factors.
That makes sense. And then, so as you find these areas of study, I'm wondering, I know you haven't done your research yet, but will you use similar tools? Will you be using that big soil analysis machine you showed us?
Yes. Yeah. So those are, the goal is to develop these tools to use them almost identically in ancient soils.
And so how did you initially know that you should start by analyzing today's soil in order to look at the soil of the past?
Well, to be totally frank, we definitely do them both at the same time. So we don't always start with the modern and then work in the past. Often we measure soils in the past and realize that we aren't fully able to interpret their isotopic composition. And so then we turn back to modern and measure modern soils to see if we can use a place that we understand its climate, and we know the conditions under which it's forming. Okay, what does the isotope look like there? And then we go back to the past. And so they definitely inform one another. It's a fluid process where we go back and forth between understanding the modern and the past.
Mm-hmm. So I'm wondering, Laura is saying, can this climate research apply to other planets?
So I think in theory, yes. Practically, we would have to collect the samples and return them to Earth, which
right.
I know for the Mars, or there is a Mars mission that's working on returning samples to Earth for analysis, which will be really exciting. I don't think the Earth will probably remain a solid body, so it might not necessarily become something like Venus in the future. But there are people who study places like moons, icy moons of Jupiter, to understand early Earth, which is kind of the opposite of what this question is exactly. But we look at kind of other extreme environments in the solar system to understand Earth's past rather than to understand Earth's future.
Mm-hmm. That makes sense. And so I'm wondering if you can tell us a little bit about your educational path and how you got to where you are now. I know that your field of study is quite specific. How did you refine it to become something that you're so passionate about that's so specific?
Yeah, that's a good question. So when I started in college, I didn't exactly start knowing that I wanted to study geology, but in a couple of years, I realized that I was really passionate about studying the Earth, both because of the obvious implications for our human residence and human effects on the climate, and because the Earth, the landscape that we live in, affects pretty much every bit of our daily life in ways that we don't fully appreciate. So I think that motivated me originally to study Earth science. And then when I started my doctoral research, my PhD at the University of Washington, I kind of zoomed in on this really narrow part of geology where I was I was initially interested in climate science. And then part of what I work on is driven by the state of the science, like what are the big questions, what are the big outstanding questions in geology, and what can we use, and how can answering those questions help humanity? And so that has been my motivation in coming to this field of study and developing these proxies for understanding climate in the past, and especially climate on land on the past, is something that I think can address those human questions, and also as kind of an open area of research. So.
Mm-hmm. And I'm wondering if you can share a little bit about your day-to-day research. I know that you got to spend some time in the field, and we've heard from some scientists who spend a lot of time in the lab. It sounds like you kind of have to balance both.
Mm-hmm.
What does your work look like?
Right. Yeah, so I always joke that, another reason that I wanted to become a geologist was because I love the outdoors and I love being outside and I love the field work. In reality, I probably spend 3 weeks out of the year in the field at most, and I spend most of my time in the lab doing the analysis, and also even more of my time on the computer writing and reading, and both finding funding for this research, being a scholar, so reading papers, understanding those papers, writing my own papers for publication. in analyzing the data that I'm collecting. So, but I would, outside of computer work, the biggest chunk of my time is actually in the lab running samples.
Mm-hmm.
So this morning we had a leak on that big machine, and I took apart one of the reactors. This was one of the first times that I've actually had to wear like full PPEs with a face shield and a lab coat, not just because of COVID, and we're taking it apart and putting it back together. So sometimes it can be quite mechanical. Oftentimes it's not. But
is that big machine standard in other labs, or is it specific to the lab that you're in?
No, it's far from standard. That's specific to the lab that I am in.
Fascinating. Quite interesting. I loved seeing all the intricate parts. It was really great that you talked us through that photo there.
Yeah.
So we're going to wrap up soon, but I wanted to know, to maybe kind of leave the audience with something that they can do. I noticed that some of your most recent field research was in fairly close together areas in California, Livermore, Sierraville. They're not really that far away. Is this kind of research something someone could go do, maybe in their backyard, and then drive a couple hours and look at some other soil? They wanted to just kind of get a beginner's experience.
Yeah, absolutely. Especially in California, it's kind of an interesting place to study how soils develop in relation to climate, because there are such different climate states within driving distance. So even the San Francisco Bay Area has kind of a microclimate, where San Francisco itself is quite cold and foggy, and then you go over the Bay Area hills and you're in the Central Valley, and it's hot in the summer and drier. But absolutely, you could go dig a soil pit, or even just look at road cuts of soils, and probably observe for yourself that the soils that form in those different climate states are quite different than they are. Yeah.
Mm-hmm. Great. Well, if you're watching, go dig a soil pit. If you're a little kid, ask your parents first. But Dr. Julia Kelson, thank you so much for being here. We loved hearing your research and watching you present. And I hope you have a great day.
Awesome. Thank you.
Thank you.